And here is the second most common motion when it comes to motion within a plane or in two dimensions. It's the circular motion. When we have an object that moves along a circle. We'll focus right now on uniform circular motion. In other words, when the object is moving in a circular path at a constant speed. We will have a chance to look at what happens for non-uniform circular motion later in the module on rotation. The distance here given in meters most often is counted in terms of revolutions, so we'll have the distance for one revolution to be simply the length of the circumference of that circle equal to 2 pi r. Here little r is the radius of the circle. We have two new concepts here. We're introducing the period t, which is defined as the time for one revolution, and the frequency f, which is the number of revolutions per unit time. The two concepts here, period and frequencies, are always used and handy in situations when we have a repetitive motion. In this case, the object going along a circle just repeat its motion over and over in terms of rounds around the circle. The frequency and the period are related because of simply the way they're defined. Their definitions always ensure that the frequency is equal to 1 over the period. Now let's look at the speed. Remember, speed is simply how fast the object is moving. Given that the object is moving at a constant speed here, we can use the formula for the speed equal to the distance over time. And once again, for one revolution, that speed is going to be equal to the circumference. The distance for one revolution is the circumference of 2 pi r divided by the time for one revolution, which we introduced as the period. Remember, speed and velocity are different. Velocity, it is true that the magnitude of the velocity is going to be equal to the speed, but the velocity concept has a vector nature. In other words, it is a vector, and so for the circle here, as the object goes around the circle, that vector will change its direction. Let's draw the vector. The vector is always tangent to the trajectory, not only for the circular motion, for any type of motion. If you draw the trajectory and you know the path along which an object is moving, the velocity vector will always be equal along the tangent at any given point. The magnitude of that vector will be the speed. So here we see that even though the speed does not change and the object is moving in a uniform manner around the circle, the vector itself changes. In fact, it changes constantly. The changes are always inward for that vector. So we are going to have an acceleration associated with this motion, which has a direction towards the center of the circle, to account for the fact that the shift in the direction of the velocity vector is always inward towards the center of the circle. The magnitude of that acceleration turns out to depend on the speed and the radius. In fact, it's equal to v squared over r. Because of the direction of that acceleration pointing always towards the center of the circle, it is called a centripetal acceleration.